Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with integration, looking at infinite and improper integrals. So if you're ready to learn, then let's get into it. So to start with, what is an infinite integral? Well, it's where we have a positive infinity or negative infinity in the upper or lower, respectively, limit. So for example, what does the integral of a to positive infinity of a function f of x dx actually mean? So to decide whether this actually has a meaning, we write that a function I of a number n, we define this as the integral from a to n of our function f of x dx. So as n increases, our upper limit of this integral also increases. And if this has a finite limit as n tends to infinity, so if in tends to a finite number as n tends to infinity, then our infinite integral exists. So for the first example, let's look at e to the minus x and having a positive upper limit of our integral. So this would be the limit as n tends to infinity of a to n of e to the minus x dx. And that's the limit as n tends to infinity of e to the minus a minus e to the minus n. And obviously, as n tends to infinity, e to the minus n tends to 0. So we're just left with e to the minus a, where a is just our arbitrary number and it's also a finite number. And so we have a finite integral, even though our upper limit is infinite. So therefore, our infinite integral exists. For our next example, we'll look at the integral of 1 over x dx from our constant limit a up to our infinite limit at the top. So we'll do the same process. This is the limit as n tends to infinity of a to n 1 over x dx. And again, this is just going to be the limit as n tends to infinity of the result of that integral, which is just log of n minus log of a. But a log of n doesn't tend to 0 or doesn't tend to a finite number as n tends to infinity. I'll write that formally, that log of n tends to infinity as n tends to infinity. So even though our log of a is a constant, we're going to still result in this tending to infinity as n tends to infinity. Therefore, our infinite integral, in this case, doesn't exist. In a similar fashion, if we turn our attention to improper integrals, they're very similar in some respects, and these are defined as where we have a singularity of the integrand on the range of the integration. So that could be at either endpoint, so the limits of our integration, or it could be within this range. How are we going to resolve that as we integrate it? So let's start with an example of the integral from 0 to 1 of 1 over the square root of x by dx. And this is, if you look at it graphically, got an issue with our integral. Our potential problem is that x to the minus a half becomes infinite at the endpoint x equals 0. This goes off to infinity. And so a way we can resolve this is to integrate from epsilon to 1, where our epsilon is between 0 and 1, but it's very much smaller than 1. And that's what this double smaller than symbol means. It's much less than. And then, once we've done that, we then take epsilon tending to 0 to find our final integral of 0 to 1. So if we look, now we will have, instead of I of n, we'll have I of epsilon. And in this case, it will equal integral from epsilon to 1 of x to the minus a half dx. And that is equal to 2x to the half with our limits 1 and epsilon, which equals 2 minus 2 square root of epsilon. And then as we take the limit of epsilon tending to 0, so limit of epsilon tending to 0 of I of epsilon, this is equal to the limit as epsilon tends to 0 of 2 minus 2 square root of epsilon, which will just become 2. In this case, it's fine, our improper integral can be calculated, and we have a finite area. So if we look at another example that's quite similar in some respects, 1 over x squared dx, with the same limits, 0 to 1, graphically looks similar from how I've drawn it. But if we follow the same process, so skipping some steps of writing out I of epsilon and stuff, limit as epsilon tends to 0 of epsilon to 1 of 1 over x squared dx. That's basically all these lines into a shortened version. We then will get the limit as epsilon tends to 0 of minus 1 over x from epsilon to 1. And this is the same as limit as epsilon tends to 0 of 1 over epsilon minus 1. And that obviously will tend to infinity as epsilon tends to 0, 1 over epsilon is tending to infinity. So here we have infinite area. It doesn't resolve. And so our singularity at the endpoint of 0, our lower limit, is an issue here. And so we don't have an integral. There's no area representation, it's infinite, for this function from the limits of 0 to 1. So as an extension to this last example of 1 over x squared, we can imagine if someone wanted to calculate from minus 1 to 1 of 1 over x squared dx, we're going to end up with just minus 1 over x from 1 to minus 1, and that will just result in minus 2. And this, from just looking at the maths here, doesn't look like there's any issue. But obviously, looking at our graph, our area can't be negative. It's going to be a positive number, firstly. And secondly, we know there's this issue that if half of that area from just 0 to 1 is infinite, how are we getting a finite negative number from minus 1 to 1? And so, again, the trouble is because of this singularity at x equals 0. So instead, we should have written the integral from minus 1 to 1 and split that up into the integral from minus 1 to minus epsilon 1. So this will be a number very close to 0, but just below 0, plus a number just above 0, epsilon 2, up to 1. And epsilon 2 would be the same as our epsilon here, and epsilon 1 will just be the negative inverse of that. It doesn't matter, we're going to be tending these both to 0 to find our final answer. So then epsilon 1 and epsilon 2 tend to 0. And if we do this, it does indeed result in our infinite area, as we'd expect. So be careful to check, are there any singularities in the function that are going to screw up my integral here? And if you can find any, then try and follow this procedure to eliminate any issues and see, well, no, this integral does not exist. There's an infinite area under that part of the curve, so you can't give an answer for it. Today, we've looked at infinite and improper integrals. In the next video, we'll be looking at some useful techniques to use for the more tricky integration calculations, including partial fractions, substitution, and integration by parts. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.